Okay, so we're going to have a look at Cauchys Integral Formula in this video. So what we're going to do is we're going to try and integrate this function here, exponential of 3 minus z over z with respect to z, over the contour gamma. Now we've got gamma is, z is absolute value of 1. So let's just draw that on the complex plane for now. So for z equals 1, we've got something that looks a bit like this. That's the imaginaries, and that's the reals. Okay, so we've got 1.1 here, and the point I here, minus 1 and minus I. Now this is a simple closed contour inside the complex plane. So that's a simple closed contour in the complex plane, and the complex plane is a simply connected region. Okay, so how are we going to go about integrating this function now? So what we want to do is, using Cauchys integral formula, we're actually not going to need to integrate. So what we do is we find the singularities and the points where this function is not analytic. So at the point z equals 0, this function here is analytic. So therefore, if we substitute in for z equals 0, we can find a solution to this using Cauchys integral formula. So we've already looked at the rules for this. So the complex plane is a simply connected region, and we've got a closed contour here, gamma. So we just put gamma in here like this. So all we have to do now is to say the integral on gamma of exponential of 3 minus z dz over z equals 2 pi I times, and all we have to do now, this will disappear because for z equals 0, and we just plug in 0 for this z here. So we put exponential of 3 minus 0. So then all we're left with now is 2 pi I e to the 3. So 2e to the 3 pi I. So by Cauchys integral formula, just write that one here. That is the solution to this integral. That's a nice way of doing an integral without actually doing any integration at all. Okay, so we've got an integral here, and we're going to try and use Cauchy's theorem to integrate this function here. So we've got e to the z over 4 minus z cubed with respect to z, and the parameters of integration are the contour gamma. So gamma is defined as the modulus of z equals 2. So let's just quick draw that up on the complex plane. So that's the reals, that's the imaginaries, that's the origin, and z equals 2. So this point here will be 2, this point here will be minus 2, this point here will be plus 2i, and this point here minus 2i. Okay, now this region here, this one gamma, we can see that this is a simple closed contour, and it's inside the complex plane. And what we could do, we could put that inside another simply connected region, which would give us a radius or a modulus of 3. Okay, so that's a radius of 3, this region here. So what we can say is that all the points inside gamma are contained in this point here and the complex plane. So there are rules for Cauchys theorem. So Cauchys theorem. So the rules for the Cauchys theorem are now all satisfied. Now next what we've got here is 4 minus z cubed. So what we're interested in now is 4 minus z cubed equals 0. So obviously that's the case when z equals 0. Z equals 4. So when z equals 4, this function here becomes analytic. We can't it's undefined. But when we're dealing with Cauchys theorem, that's the points that we're interested in. So the z equals 4, that's going to be somewhere out here. That's the point 4. Now, as that point 4 is not contained within gamma, what we can say is that the integral across gamma of e to the z over 4 minus z cubed dz equals 0. And that's a very easy way of integrating that function across the contour gamma without actually doing any integration. Okay, so now we're going to look at Cauchys integral formula, and in particular Cauchys nth derivative formula. Now, the integral we're trying to do is exponential of 3 minus z divided by z cubed with respect to z across the contour gamma. And gamma is where modulus of z equals 2. So let's just draw that on here so we can see what we've got going on. That's the reals, that's the imaginaries, and that's the point 2, minus 2i, and 2i. So this is our gamma. Now we can see that this simple closed contour is in the complex plane is fully contained within inside, and we can also say that this region here is contained within this part here. So we can say we have a simple contour, and we can call this radius 3i, so 3. So that's modulus 3. Okay, so now what we need to do is we need to find the singularities of this function. So the singularities of this function is quite easy to see. So singularities are at z equals 0, and you can see it's a pole of order 3. Okay, so now what we do when we use Cauchys nth derivative formula, so we use Cauchys nth derivative formula. So what we say is that this integral here across gamma exponential of 3 minus z over z cubed dz, that equals 2 pi I, and then we divide it by 1 less than the order of this, factorial, so we divide it by 2 factorial, and then we multiply by this function here. So let's say, let's just let f of z, let's just write that down, right down here, f of z equals exponential 3 minus z. So now what we need to do is take the second derivative. So the second derivative of z, and we take it at the point 0. So here we've got 2 pi I over 2. Now the second derivative of this, so first derivative, exponential of 3 minus z, just write that in, the input doesn't change. But now by the chain rule, we need the integral of the derivative of minus z, which gives us minus 1. Now we've got to take the second derivative of this point z. So we've got minus exponential 3 minus z. Again, the input doesn't change, but now we take the derivative of minus z, which is minus 1. So now we end up with a positive. So now what we do, the second derivative at 0, 3 minus 0 is just 3. So times exponential of 3. So that will equal, that one can cancel out, e to the 3 pi I. And that will give us our answer using Cauchys nth derivative formula. Okay.